So in this video, we're gonna look at sets. All right. So all right. So here, in a very just definition of a set, just very broad, it's an unordered collection of elements. All right. So some very famous sets are the set of natural numbers. Right. So we think of 0, 1, 2, etc. Right. Now, some textbooks do make a distinction within what's called a natural number and a whole number. Sometimes leaving out the 0. Our textbook, and I'll also use a convention that the natural numbers begin with 0 as opposed to 1. All right, and then another set here is the set of integers. So here, right, 0, 1, 2, etc. All right, and we also have the set of rational numbers, which we define here as AB, such that AB are elements of Z, right? That that notation we're familiar with, that E, that little kind of rounded out E, is an element of Z, right? So the rational numbers there are defined using set builder notation, where we have just kind of an example of what a element would look like. And then this bar, right? The way you read that is the set of irrational numbers, which you call Q, is A over B, such that A and B are both integers. All right. And then we have R, which is the set of all real numbers. There's no set builder notation here, and it has a lot to do with just kind of the way that the real numbers, are defined, right? They're what we call uncountable, right? So we can't really put them in order, right? So there's no way to kind of write a set builder notation, and we just state that it's the set of all real numbers. Now we also have irrational numbers. Now sometimes this isn't standard notation, so not all textbooks use this. I came across it in a couple of stuff that I was reading. They use the I, but again, not standard. Here I'll just make explicit that I is irrational, and one way you can think of it is it's R minus Q, right? Sometimes written as R, and then this slash, your backward slash here, is without Q, right? The real numbers without Q. Okay, and we'll get more into that and when we do proofs in terms of the types of notation. All right. Now, all these examples are examples of infinite sets and different types of infinity, which we won't really think about the types of infinity, right? The natural numbers and the integers; those are both infinite sets, and even the and even the rational numbers; those are both infinite. But we do have a way to kind of we use a set builder notation to write these out, right? That is kind of not allowed to do with, or not able to do, I should say, to the real numbers or the irrational numbers, right? Just because of the nature of them and how there's just actually a significant amount more of them. Okay? All right, now a couple of basic operations that we can do with, or how we can describe sets. We can describe the union of a set. Right, so again, using Venn diagrams here as an abstract notion, A and B, we can say the A union B is either the set is an element of both A and B, right, or of only A, or of only B, right? So it's in either or, right? So A is an element of B, or A is an element of A, then A is an element of union A union B, right? So that encompasses everything, right? Right. We can think of here right? The set, the union that defines the rational and the irrational, that would be the real numbers, right? Okay. Now we also have, on that same vein, the intersection, right, which we define A intersection of B, right? So here, if this is set A, this is set B, the intersection is what is in both of them. So for, if let's say A needs to be an element of A and A needs to be an element of B in order for A to be in the intersection of A and B. Okay. All right. Okay. Now, if we take the previous example here, we looked at the irrational and the irrational. Right? Well, there's no number that is both irrational and irrational. So there is nothing that is overlapping, right? There is no A that is both element of Q and I. So when something like that occurs, right, we use this notation, right? This is called the empty set. Okay. All right. So now another way to describe this is in terms of subsets. All right. Okay, so the subset, so the definition of a subset, I'm saying here, so we say A is a subset of B, and usually written like this, provided for all A element of A, then A is an element of B. Okay? All right. Now, even further to that, we can define the idea of a proper subset, right? Because with this statement, right, it would not be incorrect to say R is a subset of R. Okay? Right? That would hold with the statement given above. Okay? So we define further this idea of something called a proper subset. Right, which usually we use this notation, right? So there's no like mark below if it is a subset of B and A does not equal to B. Now, here this notion of equality for sets, right? How do we define that? The way we define that is that in order for two sets to be equal, all the elements of A must be in B as well. All right, so that means that if this were not to happen, there must exist, right? There exists a B element of B and B not in A. Okay, so this set B is somewhat bigger than A, right? And it contains at least one more element. Okay, so that's the idea of a subset. All right, a subset and a proper subset. Okay, so here, a proper subset of the real numbers, we could say, all right, well, Z is a proper subset of the real numbers, right? The natural numbers is a proper subset of Z. Okay? All right. And then this kind of relation here that we set up here also leads us to our kind of our transitive property of sets, right? So another property of sets is that for any set, sets A, B, and C if A is a subset of B and B is a subset of C, then A is a subset of C. Right, we can kind of follow that around here, right? So if we look here, if the natural numbers are a subset of the integers, if the integers are a subset of the reals, right, then here we can conclude from our definition below, the naturals are a subset of the real numbers. Okay. All right. Now, here to prove this, right, we could start by saying here, so let's do a proof of this statement here. Now, how would we go about proving this, right? So I'm going to try a direct proof, right? And a good place to start is always to, let's take a look at, we'll start with all of our assumptions, right? So here we assume that A, B, and C, we are given sets A, B, and C. I don't know anything about them, I just know that they are sets, right? Given sets A, B, and C. Okay, and A is a subset of B, B is a subset of C, right? Those are our hypotheses. That is what we can assume to be true, right? If we take it back all the way through our truth tables, right? This works here, right? We only care about when the hypotheses are true, right? And I want that to lead me to a true conclusion, right? That would make this a valid statement, right? Valid implication. Okay. So we start with the fact here. Let's let X be an element of A, right? Any element of A, right? Now, by assumption, A is a subset of B, right? Therefore, we can conclude, so this leads us to say X is an element of B. All right, that's by our assumption. All right, but also by assumption, since B is a subset of C, right, then X is an element of C. All right, now this is value of X was arbitrary, so it could be any value of any element of A. So any element of A will also be an element of C. So therefore, we come at our conclusion, A is a subset of C. All right, and that is how we show this proof here. All right. Now, one thing to notice here that we don't have any kind of description for A, B, and C, right? So one thing to kind of clear up here, just to like, as a fact of sets, we can say here, or it is true that the empty set is a subset of any set. Okay, so for this A, B, and C, they all three of them have a subset of the empty set is a subset of them. All right. Now, here this kind of ties together all make sure that our theorems capture the fact that we're given A, B, and C, but what if one of them was empty, right? What if all three of them were empty, right? Then that doesn't affect the implication there, right? That still holds, right? If you go back, look at all these definitions, right? That would still hold, right? Okay. All right. Let's do one example here. Right, so here we want to prove that every multiple of 9,100 is also a multiple of 13. All right. Okay. So looking at this, all right, well, how can I do that right now? Again, when I say a multiple, right? So let's define a set A to be the set of multiples of 9,100. Right? Now what that means is that we can have using set builder notation, right? We have this type of behavior, right? It's 9,100 times k, where k is just any integer, right? That would be a multiple of 9,100, right? So we can have B to be the set of multiples of 91. So what that means is that I can write B as 91J, where J is an element of Z. All right, and then C here, set of multiples of 13. In other words, I can write this as 13L, such that L is an element of Z. Okay, so if we let's start with A, element of A. That means that A has to be written in the form of 9100K. But this is also 91 times 100K, right? And again, properties of integers here, right? Any integer multiplied by another integer is an integer. So this I can write as 91J. So that tells me that A is an element of B. All right, going further here, I can write 91 as 13 times 7 times J. Okay, and then again here, right, the closure here of integers means I can write this as 13L, and that implies that A is an element of C. Right, and now we have that, again, A was arbitrary, right? It's any multiple of 9100. Well, any of those will also be a multiple, as we see, of 13, right? So now we have proven here from our above statement here that A must be a subset of C. So all multiples of 9,100 are also multiples of 13, right? This type of structure here is what our book calls element chasing, right? Where you kind of set it up where you want to show each one is a member of the other subset.